All right, I think we're live. It looks like as of right now, there's no one else on, so I'm gonna just wait and hang out here till I see if there's another viewer. And so feel free to hop in or out at any time between now, which is 1:30 and 2:30, and I'll answer any questions you have. Again, you can use the chat window built into the YouTube, Google Chat, Google Hangouts chat, or you can just send me an email and I'll be monitoring any emails I get throughout the hour. So as of right now, I'm just going to see if anyone. All right, I will talk to hopefully some of you soon. Hey, I realized that I didn't have the video on for the first bit, so there still isn't anyone on, but I just want to welcome you to the office hours for chem slash astronomy slash biology slash whatever six at Tufts University, Big Bang to Humankind. I'm Dr. Andrew West. I'm leading the astronomy portion. I just wanted to welcome you to office hours and remind you that you can text your questions or chat them in the chat window that you should be able to see on your YouTube or wherever you're accessing this. But you can also send in emails to me. Either way works. Happy to answer any and all questions. So I see that someone is on. Feel free to ask questions as you have them, and I'll answer them live here until about 2:30. All right, so I'll just hang out and wait until we get the first question. Oh, someone popped out. All right, I am gonna mute things just for until I get some questions. So if anyone's out there and has some questions, feel free to again write them in the chat window or send me an email, and I'm happy to answer them live here on this Google Hangout. So I will mute things until I see if there are some questions. few people have come on. This is your chance to ask any questions you want. They can be about the class, specific things that maybe have seemed confusing, things about astronomy in general, things about my research. Uh, Pretty much anything goes. That's the beauty of office hours, whether they're in person in one of your professors' offices or kind of virtual like this one. So, a few of you have come on, but I haven't seen any questions come in yet via the chat. So, if you um, come back on and want to ask a question, please do. Otherwise, I'm gonna keep it muted, but I'll be here, like I said, until about 2:30. Okay. I see someone's on. If you have a question, please type it in the chat window or um, send me an email, and I'm happy to answer anything. I'm gonna still stay on for another 20 minutes or so, so happy to answer whatever you have. I'm both checking the chat window and email, see if there's any questions. So feel free to send me something if you have it. Again, questions can be anything from class, some concept that seemed a little confusing or we went over super quickly, or really anything from astronomy. You can ask me about the research that I've done. Um, any of that is fair game, and I'll do my best to answer. So, again, questions via email or in the little chat, which I think you should see if you're in YouTube or in Google Hangouts. There's like should be a little chat window. If not, just send me an email. Okay, I'm gonna mute it until I get a question. Um, and all right, hope to hear from some people. Awesome. So I just got a question from Evan, and Evan asks about the CMB or the cosmic microwave background. So hi, Evan. Um, and really what is its significance. So I'll start at the beginning. There are a couple things on why it's significance, and I'll remind you a little bit about what it is. So um, the cosmic microwave background, thing that it's the most significant is that it was a direct prediction of the Big Bang theory. So um, at the beginning of the 20th century, people like Edwin Hubble discovered that the universe was expanding. And so people kind of hypothesized that if the universe was expanding, it was once much smaller. And if it was once much smaller, it was going to be hotter. And there were lots of other physical consequences of the universe being smaller. And so um, what what they did is they said, okay, if the universe were smaller and hotter and had all these different properties, where would what are some predictions? And so one of the things we talked about was like the number of neutrons, the amount of helium that's made in that first 3 minutes ends up being one of the predictions. But it turns out even in the first several minutes, or even several years, or even several hundreds or thousands of years, the universe was so small and it was so dense. It was like a thick cloud, and no light, even light that was generated, couldn't get out. It couldn't actually propagate. It was just hitting around, and it took for the universe to expand and get much larger for it to now become be able to see through, become at least translucent a little bit, for light to start to escape. And the moment that happens, it turns out we didn't talk about this, but there's something physical that happens. It's actually that the universe gets cool enough that the electrons that have been spinning around and the protons, because most of the universe is just hydrogen, were able to actually stick together finally, cool down, that the universe no longer was a plasma like the sun is. but actually you could have individual hydrogen atoms. And that immediately made the number of particles cut in half. You went from having protons and electrons all floating around to just having hydrogen atoms. And all of a sudden that cleared out the universe. And now light could pass in between those atoms where it couldn't before. And that was predicted that there would be this moment where you could finally see light that was left over from the early universe. And so these researchers, mostly at Princeton, but to be honest, all over the place, were looking for this in the 60s. They predicted that it should be everywhere you look in the sky should have this glow, and this glow should have a certain characteristic. It actually has characteristic of a certain temperature, just like we learned that hot stars are blue and red stars or cooler stars are red. If you had something that's really, really cool, like super cold, everything still has temperature. Anything with temperature still gives off light. And so it turns out really, really cold things give off light still, even if they're in the freezer. They give off light in the radio wave portion of the electromagnetic spectrum. And so they predicted that this background would have a temperature that's about 3 degrees Kelvin. So super, super, super cold. That's like negative 270 degrees Celsius. So super, super cold. And so they actually went looking for it. But in order to like actually see it, you had to have really sensitive radio telescopes. And that was actually an era in the 60s where radio telescope technology was really taking off. And so it turned out this other group that I talked about in class, Penzias and Wilson, who weren't looking for it at all. We're just trying to build really sensitive radio receivers. Actually picked up this signal. It just looked like noise to them. It was signal that was coming no matter where they pointed their telescope, basically. And so just the discovery of it is hugely significant. I mean, it was additional confirmation of the Big Bang Theory. Again, something that had been predicted, and predicted to be a very specific characteristic. Not only was it found, but it actually had that exact characteristic that was predicted. So it was really cool. But it turns out that, as I showed in that image in the lecture, that even though it's basically about 3 degrees, it's actually 2.7 degrees Kelvin. That's the temperature all over the sky. It actually fluctuates a little bit at kind of really, really small levels, like 10,000ths of a Kelvin. So there are tiny fluctuations, and those tiny fluctuations, the size of them and the amount of them, both the physical size and the temperature fluctuations, like how much they fluctuate, actually gives us important information about a bunch of uh, aspects of the early universe. They tell us something about how much dark energy is in the universe. They tell us something about how much dark matter is in the universe. They actually even tell us something about the normal matter that we call baryonic matter. Um, they tell us something about that. They also tell us something about the curvature of space. That's not something I talked about, but it turns out that when I was in college learning about cosmology, we actually didn't know that the universe was accelerating. That didn't happen until actually right as I was graduating from college, or maybe my junior or senior year of college. We first learned that, the first evidence of that. But when I first got to college and was learning about cosmology, one of the things that was a big question was, is the universe what was called flat or curved? And a way to think about this is, there actually is a possibility that the shortest distance between two objects in space is not a straight line. That maybe it's like we're sitting on a big cosmic globe, right? And if you're like walking on the globe, if you're walking from even Boston to Seattle, I used to live in Seattle, Washington, and so the shortest distance is not just to draw a straight line. Actually, the shortest distance is to actually curve up over north, actually up over Canada, into almost the Arctic and go to Seattle. That's the shortest path. And so there was actually a possibility that the universe was like that as well, that distances in the universe traveled along curved paths. It turns out that from the cosmic microwave background, that actually doesn't seem to be the case. It seems to be that we live in what's called a flat universe, and that the geometry is, shortest distance between 2 points is a straight line, which is a little comforting. Um, but it does mean that we have this dark energy stuff. So I don't know. I hope that helps. Send me another question, Evan, about the cosmic microwave background if uh, that doesn't help. I see there's other people online. So if you have other questions, again, either send me an email or send me a chat. If you're using Google Hangouts, you can just use the chat feature. If you're on the YouTube site, which I sent the link to, there's actually a way to chat in there, and I should be able to see it in there. I haven't seen any chat. So, oh, sweet. Evan just sent me another question. Okay, Evan asks, do we just see these images by looking as far away as we can, far back in time we can, like ignoring all the stars and seeing the colors at the very edge? So the question is, when we go look at the cosmic microwave background, do we just look as far away as we can, and whatever's left is the cosmic microwave background, and we ignore everything in front of it? That's exactly right. So we basically, when those observations of the cosmic microwave background are taken, the image I showed you has had things like all the stars in our Milky Way subtracted, the actual disk of the Milky Way subtracted, all of the foreground galaxies. So you're not only looking through the stars in our own galaxy, but you're looking through all the other galaxies. So all of that has been subtracted from that, and you do that by actually using different telescopes to say, "Ooh, I know there's a galaxy there, so I'm going to subtract that out," or "I know there's the Milky Way here, I subtract that out." And right, all you're left with is this light that's kind of glowing no matter where you see in the sky. And literally that image that I showed you in the lecture is a global projection. It's literally assuming that the sky is like a globe, or it's the projection of the globe, the Earth's globe, onto the sky. And so that literally is everywhere you look is the cosmic microwave background, which is pretty cool. I mean, it's a pretty neat thing. So yeah, that's exactly what it is. It's the farthest thing away that we can possibly see right now, and that's just because, um, really, because anything farther, of course, would take more time to get to us, and the time that we can see back to, which is when the universe was about 3 to 500,000 years old, so not very old cosmically. Um, that's this moment where the universe gets diffuse enough for light to pass through the in this case atoms, and starts shining out. So awesome question, Evan. Um, Great. Any other follow-ups or other questions? Again, anything is fair game. And I'm happy to start, even though we're approaching 2:30. If there's more questions, I'm happy to stay on for another 10, 15 minutes if there's more questions. And like I said, I'm going to try to do this again Friday if people want to. There weren't a ton of questions today, but there were some really good ones. So happy to do this again. Um, and like I said, I'm happy to stay on for another 10 or 15 minutes. I'm actually here at home, and my son, who's 18 months old, is sleeping upstairs. So unless he magically wakes up, which he shouldn't, I'm just chilling here. So I'm actually finishing up tomorrow's lecture. So uh, happy to send me more questions if you have them. Again, in the chat, if that works. I haven't seen any in the chat. I'm hoping that we're all on the same page there. But if the chat hasn't worked, then just send me an email. Again, I'm constantly checking my email, have it pop up if you have any questions. So um, send more if you got them. Like I said, I'm happy to stay on until like another 10, 15 minutes if people are interested. We've got a few people on right now that I can see are viewing. So happy to get answer more questions. Again, and anything's fair game. Oh, awesome. Oh, just thanks for Ellen. You're welcome, Evan. Um, if you're still on. Other questions? Anything? Again, it can be about the class. It can be about anything in astronomy in general. Um, Again, this class only touches on a few tiny pieces of astronomy, kind of what I thought the fun highlights were for a class like this. But there are a lot of things that we don't cover at all, or I maybe cover in just one sentence. Um, and some of those actually can turn on to be a whole class. So again, let me know if you have any questions. Uh, Happy to stay on. I'll stay on a little bit longer um, for those who are viewing right now. Um, I'm not seeing any chats, so if you've chatted, sent me a chat, I'm not getting them. Um, but the email is working. I got email from people for questions, so send me the email. Again, I'll probably mute the microphone until I get another question. But again, I'll stay on for another 10, 15 minutes. I see there's someone still on, so if you have a question, send me a note either in the chat or the email, and I'll answer it. All right, thanks. Awesome. Question here. Let me get it here. It's from Isabel, um, who asks. I think. Let's see if can you still. Yeah, you can still see me. I think I remember that dark matter is invisible and its effects have been recorded really far away. But could it be all around us? Totally. So, Isabel, that's a great question, and that's totally the case. So, dark matter, we think, is kind of permeates everywhere. Now, it still clusters in galaxies, and what I mean by that is galaxies are collections of matter, both kind of normal matter, like you and me, but also dark matter. But the distribution of dark matter throughout a galaxy is pretty um, at least continuous. It turns out that there's a little more dark matter in the centers of galaxies, and as you expand actually spherically around the galaxies, the amount or the density decreases a little bit, but it's very continuous. So what that means is inside of galaxies, individual galaxies have big pockets of dark matter, as a bulk system. But that means there could be dark matter floating around in my living room right here, where you are ever watching this video. Um, Now, it turns out if you calculate, even though 90% of of the mass of the real mass of our galaxy, just the Milky Way, is dark matter, only 10% is made up of things like atoms that we know of. Um, the uh, the oh, it looks like I just lost my viewer, so maybe that wasn't Isabel. But anyway, I will. I'll finish the question for anyone who watches the YouTube afterwards. So even though 90% of the dark matter, or a galaxy's matter is dark matter, and 10% is just atoms and normal stuff like us, the density of dark matter, like in our own solar system, is minuscule. So yes, there is some dark matter, but it has no influence over like any of the gravitational pull of the sun on the planets, or the planets on moons, or planets on planets. Has no influence whatsoever. So in terms of detecting it, again, we don't know exactly how that worked. There is some maybe evidence that there's been some, what I had mentioned, these gravitation or these dark matter annihilation events where dark matter particles, one of normal dark matter and one of anti-dark matter, again, whatever it is, collide and produce some kind of late event. There's been some evidence that maybe people have started to see that, but nothing conclusively. Um, Once it's conclusively discovered, again, this will certainly win the Nobel Prize, because it's a huge discovery that has baffled astronomers for almost a century now. I mean, at least many decades, but it's been a very long time since there's been evidence of dark matter, and unfortunately, it never keeps going away. So I think someone will discover exactly what this probably small particle is, and whoever does that, or whatever team of people do that, will win the Nobel Prize. Um, and that said, it's unlikely that we would see one of these annihilation events like in our own solar system, just because the density of even regular dark matter is so tiny that interacting with a single dark matter particle probably is very unlikely. Let alone having one interact with um, an anti-dark matter particle, whatever that is. And again, we don't really know exactly what the density of those are at all. And it very well could be that some of these annihilation events that people have seen are not dark matter, are not like individual particles, but could be collections of particles. Again, we just don't know the answer. This is a question that's like right at the limit of our understanding. So awesome. Okay, I am going to. Doesn't look like anyone's on right now, so I'll stay on for a few more minutes just to see if there's any stragglers. I'm gonna mute the microphone, and then I'm gonna type an answer to Isabel's question. And if there are other questions, either in the chat or on email, I'll start up again and again. I'll stay on for another 10 minutes or so. Okay. Oh, looks like there's one more person on. Um, I was going to sign off here in a minute or so, so I'm happy to answer one last question. You can either send me a note in the chat or send me a email in the next minute or so. I'm happy to answer one last question. Otherwise, can save more questions for tomorrow during class. And I guess tomorrow in class, I'll ask if people are still interested in me doing this on Friday. It's totally easy for me to do and set up. And if people will use it, I'm happy to do it. So whoever's on, if you can send me a question if you have one. And if I don't hear from you in the next few minutes, then I'll assume you either don't have a question or that you are going to save your question for a later time. So I will wait here for a couple minutes to see if I get said question. Um, and maybe it's Isabel who I just answered question via email, but I answered her question earlier in the Hangout. Oh, awesome. Just got an email. Um, cool. No, it's not a new question. So anything more? And I'll wait. I'll wait one more minute and see if anyone else came on. And if so, I'll answer a question. And if not, I will see people tomorrow. So one more minute. I'm going to mute it until I get another question. Mute. One thing I just noticed was that Evan, and it must have been Isabel, sent me chats via the YouTube link. And for some reason, that's not linking to the interface I have here, which is the Google Chat interface, which is very funny. Those are supposed to talk to each other. Basically, like, Google and YouTube now are all owned by the same parent, I think. And so we're supposed to link. So I don't have those chats here, but I can actually see the chats over here. I can see the questions that Evan asked me about the cosmic microwave background, and I assume this is Isabel who asked about the dark matter question. So I guess if we do this again on Friday, I'll make sure to monitor those questions on the chat on the Google side. Now, in fact, I'm gonna oh, I'm gonna do that right now. See if I can sign in can't do that right now. All right. Well, I think this is long enough. But, sign off. I will see you guys tomorrow. We'll try this again Friday. And thank you for the few of you who asked questions. And look forward to seeing you guys tomorrow and answering more questions about astronomy. All right. Take care.